Okay, 28C. Number 2. Hypothetical. In a certain town, there are about 1 million eligible voters. A simple random sample of size 10,000 was chosen to study the relationship between sex and participation in the election results. There are the results. Are they independent? So a test of independence is different, well, it's sort of different than a test against an expected value. So in this case, we have 2792 that fit in the male voted box, and 3591 that were the female voted box. And then the did not vote men were 1486 and then 2131. In the last problem we did, in the last section, we had a list of things that occurred, right? Gregor Mendel measured a bunch of plants. And then he, assuming that a certain value was true, we also had another column that was the expected value, how much we would expect to see. And then we did a chi-squared test comparing the two. In this case, I don't have an expected column, so I need to make one. Okay, so I need to figure out what percentage of the population voted. So I'm going to add up the first row, 2792 plus 3591 is 6383, and then total the next column, 1486 plus 2131, and I ended up with 3617. Now those should add up to be 10,000. We have a sample of 10,000, so let's check that. And I get 10,000. Okay, and then I add up the columns, 2792 plus 1486, and I get 4278, then 3591 plus 2131. And once again, those two column totals should add up to 10,000, and they do. Where do I get my expected values for a test of independence? So what I want to know, the question is saying, does being male make it more likely for you to be a voter or a non-voter? That's what independence is asking. Do the males vote just as often as the females? Or are the voters male as often as they are female? So what I need to do is figure out what percentage of the population voted. How would I do that? I take this and I divide it by 10,000. Now, they are nice to us. I know what the answer is because it's divided by 10,000. It's 0.6383. So what we're saying is 63.83% voted. Okay, well, how many males do we expect to be part of that voting group? We multiply these together. So 4278 times 0.6383, and that number gives us the expected male voters. How many actually voted? 2792. So I could build a whole other chart, but I like to just stick them right next to each other. And I'm going to round that up to 31. Okay. Well, and I could do that for the female, but there are two ways to do it. Either I multiply this number by 63.83%, or I just subtract. Right? I could do 6383 minus 2731. You could do 2 and then subtract the, yeah, it would work. So 3652. Before we go on, what do you think? Does being male affect your voting status? It's kind of close. More men voted than we expected, and fewer men voted than, or fewer women voted than we expected. And how do we tell if it's too much? We run a chi-squared test, and we try to land in that 5% window. Okay? What about the next row? What do I do? So I could either say 100% minus 63.83, or I could do 3617 divided by 10,000, which is 0.3617. Oh no, it died. This is bad. That's a really bad time to die. Would that, did that say Jayla? Did you name it Jayla? Uh-oh. I hope I didn't delete it. Oh no! I may have killed it. Well, hang on. I still might be able to bring it back. So I'm going to take I'm going to take 4278 and multiply it by 36.17%. 4278 times 0.3617, and I get 1547. And if you notice, this number plus this number is this number. So really, once you have one of them in a 2x2, or then you can find all of them. And then the last one, 2131 times 0.3617, and I get, oh, that's not right. Oh, I did the wrong. Hey, you're here. 5722. So 2069. Or let's do 2070. Now what do I do? Chi-squared. So I find the difference between these, square it, and divide it by 2731. Then I find the difference between these, squared, divided by 3652. And to save on time, what do you get when you do that? Did anybody, what did you get as your chi-squared value? 6.7. And then my degrees of freedom? So I delete one row and one column, and I'm left with one value. So in A106, I go to 1 degree of freedom. So I get 1 degree of freedom. 6.67 is just barely off the chart. So this is actually highly significant. So are the voting habits of men and women independent? Does being male affect your voting? They are very dependent. So does being, so yeah, if we look back at our numbers, men men vote more often in a highly statistical significant pattern. So women, get out and vote. In that area, there is a big difference. Yes. I don't know. Okay, number 3. The table below shows the distribution of marital status by sex for persons aged 25 to 34. Are the distributions really different for men and women? So you may assume that the data are from a simple random sample of 299 persons, 143 men, 156 women. To answer the question, you use which one of those? Is this a one sample z-test? No, because there are two categories. Okay, so is it a two sample z-test? No, because right. We're comparing a sample to itself. Okay. A chi-squared test with a null hypothesis that tells you the content of the box. No, because we don't have an expected set. There's no expectation out there. And we are testing for independence, so it's a chi-squared test for independence. Okay? And really, those four things are the only things that really matter in our statistics journey, is doing those four tests. There is another test called an ANOVA, which is kind of like a chi-squared test, which we're not going to get to. But if you take general stats, then you will. But it's not bad. Okay, so if the distributions are different, who are the women marrying? So we're going to take those percentages. We're going to perform a chi-squared test, right? Just like we did for the last problem. 31.5, 19.2. And we have to come up with numbers. So how many men never married? Of 31.5% of 143. So 0.315 times 143. How come I can't just compare percentages? Because there are different amounts. There are more women than there are men, so we can't compare the percentages. We have to compare the numbers. So I end up with 45 men here, and then 0.6 times 143 is 86. And then 143 minus 86 minus 45 is 12. Do you guys get that? And then 0.192 times 156 gives me 30. And then 0.673 times 156 is 105. And then 156 minus 105 minus 30 is 21. Does everybody understand where those numbers came from? I just multiplied the percentage by the number of men, and then the percentage by the number of women. Yeah. So that first column, I multiplied the percentage by 143. 0.6 times 143. Yeah. And once again, why can I not use the table they gave me? Why can't I compare the percentage of men with the percentage of women? There are different amounts of men and women. Otherwise, I should be able to do that. It should work, but we can't in this case. So now I need to figure out what these numbers are, the comparison numbers. How do I do that? I'm going to do the totals, and I know that this number is 299. So 45 and 30 is 95. So 95 divided by 299. How about 75? 75 divided by 299 is, oh my goodness. 75 divided by 299 is 25%. And I know that this is 143 and this is 156. So I'll times 143 by a quarter, and I should have made this bigger, 36. And then I need to do 86 plus 105. Oh my goodness. So 191. I'm struggling today. Divided by 299. What do I do with that number? Multiply it by 143. And then I get 91 in that box. And then this box is really easy. It's just 143 minus 91 minus 36. Right, because we only have this many men. So these numbers are what happened, but if they are independent, these numbers are what I expect. Well, they have to. The, the way we're building it, they have to add up. So take 143 minus 91 minus 36, and I get 16. Now, do I need to find the percentages for the females? No, because 36 plus this number should add up to 75. So 75 minus 36 is 39. And 191 minus 91 is 100. If you do all but one, right, all but one is all you need to do. And then the last one is 33. And 33 minus 16 is 17. Now I need to do my chi-squareds. Okay. How far is my first box off? How far off is that? Hey, I'm losing you. Come back. How far off is my first box? 9 squared divided by 36. Okay, my Abby, Bryn, plus 9 squared divided by 39 plus 5 squared divided by 91 plus 5 squared divided by 100 plus 4 squared divided by 16 plus, wait, I did it again. Divided by 16 plus 2 squared, nope, 4. Isn't it 4? 4 squared divided by 17. So my chi-squared statistic is 6.8. How many degrees of freedom do I have? Get rid of one column and one row, and I'm left with 2. So I go to A106, and that gives me 2 degrees of freedom. 6 puts me in the 5 to 10% window. So I accept the null, and I say that this data is true, meaning independent, right? Okay, so now the question. This says, so if far more women are marrying, who are they marrying? Divorced men, right? Because, well, but what it's saying is, how can the percentages be different and still be independent? Because 31% of men never marry, and 19% of women never marry. So who are the women marrying? They have to be marrying. A lot of them marry men that have been married once, and then they divorce and they remarry divorced men. Okay? Men, it appears, tend to not marry divorced women for the first time because those percentages look way off, right? Okay. 1, 3, we need to do 5. Do I need to do 5? I mean, you guys, you get it? And then 7. So 7, test whether the dice are fair. Oh, 6? Sorry, 6. Demographers think about that about 55% of newborns are male. In a certain hospital, 568 out of 1,000 consecutive births are male. Are the data consistent with the theory? What are we going to do? 1 sample z-test, 2 sample z-test, or chi-squared test for independence, or... Did we take 2 samples? No, we only took 1 sample. Okay, so is this a chi-squared sample, or is this a 1 sample? We only have 1 value, right? We only have to test 1 value. We're going to do a 1 sample z-test for percentage. Okay, so it's really easy. I think that the box is 0.551s and 0.45 right? But my percentage that I calculated is 0.568. So how do I do a 1 sample z-test? Well, I need an SD. What's the SD going to be for this box? It's the square root of 0.55 times 0.45, which I already know is 0.499 because it's really close to 1/2. Okay, so I need an SEP, which is 0.499 divided by the square root of 1,000. So 0.499 divided by the square root of 1,000, and I get 1.58%. That's my SEP. Now what? So 56.8 minus 55 is 1.8. I divide that by 1.57, and I get a z-score of 1.14, which puts me in above 5%. So I took my distance and I divided it by my SE to get the z-score. Right here, 56.8 minus 55. How far is this from that? 1.5 SDs. Okay, where is the breaking point? 1.64. So this 5% window is at z equals 1.64, and we ended up at 1.58. Do we think the assumption that 55% of kids born are male is true? Yeah. There is no statistical difference between what we recorded and what we expected. Okay?